All right, so continuing on with class 3, we're going to talk about some limiting conditions that occur in four-bar mechanisms. One that can really help you to identify an issue is this, like a tailgate right here. You can see in a truck tailgate, when these links align with each other, they form structure, especially if we're trying to move the tailgate. You can consider the tailgate as being link 2, and it can't get past this condition because links 3 and 4 have aligned. Well, there are other situations where these aligning of links cause sometimes, well, for one thing, this is not a problem. We want that to happen in the tailgate, but it can have consequences for be negative things that can happen. So we can consider these to be toggle positions, as we call them. Now, one of the less useful figures in Norton's book is right here in this section on limiting conditions right here, where they try to explain the toggle positions. So I've tried with my figures instead right here to kind of show you this collinearity condition right here. It is often when something is a non-Grashof is where we will find these to be important aspects right here. We also have stationary positions, and these could be with Grashof linkages. And we could see there could be certain locations where these will have, again, that collinearity, and they won't be as effective in those when they reach that position. So we want to be mindful of them. As you'll recall, maybe from the first or one of the original classes, we have that same issue for a Grashof linkage right here, where you could see these two align. So maybe I should use my camera right here to show this. When this is the action that we're trying to move go by, when we're using the rocker right here to drive this, so it to back drive this, and we have that limiting condition when this linkage and this linkage become collinear right there. You can see that they can't go past that, right, and even need to get kind of nudged ever so slightly to be able to get past there, right? Right, and it's also true right there. If we're lifting up right there, they're collinear again. So this is something. If we're building a machine, we have to be cognizant of these stationary positions as described here in the text. We also want to analyze the transmission angle, right? And we can define the transmission angle right here by this angle that gets placed right there. You also know that it's also this interior angle right there, and they decide to give this a mu. The idea here is that if this is the output link, let's say, and you want, and torsion is the thing that we were delivering, right? So a lot of times we want just to want a position, but a lot of times we're transmitting some force involved, right? So we have an input torque T2 and we have an output torque T4, and that you could see that only the tangential force that's being played, that's right here, only the tangential component part of this force that's being transmitted right here. Remember a two-force member, right? Remember two force members. The forces have to be in line with the thing, right? So this coupling right here can only be in tension or in compression, and the force of it is going to be in line with it. So if we're transmitting torque, the output force of this link, the coupler, onto the output link is aligned with F34 as drawn right there, and therefore only the tangential component of it creates torque because the other component is in line with the linkage. So that's why transmission angle is an interesting and important thing for us to take a look at. Now, in the book, and we have to double check on this. So even though I am going through the book with you and dealing with things, you want to make sure that you are double checking that I don't make any mistakes, because I make lots of mistakes. So I have presented in my notes available some of the things from section 4.11. So we were just in, by the way, section 3.3 called limiting conditions, where this is brought up. But I think it's relevant to our position analysis, our graphical position analysis, because now we could see what it means to be in, what the consequences of being in a particular position. That's where it's relevant. And so it gets brought up in limiting conditions, and now in section 411 we're actually told about ways to calculate it right here. So we're given this, that the transmission angle, and we have theta subscript trans, is going to be theta 3 minus theta 4. Remember that we're calculating that theta counterclockwise away from horizontal, or the positive horizontal, right? So we want to. Here are some equations that they've used with the overlapping case and the extended case of this transmission angle, and you notice that they decided to switch from mu to gamma. I'm thinking that they're saying, well, mu is the transmission angle, gamma is the instance where we have this as an angle that's less than 90 degrees, I believe they're saying, right? But when they're saying it's greater than 90 degrees, we subtract it, we get the complement angle from there, or the supplemental angle, excuse me, because we're doing from 180 degrees, so right there. So want to double check on that in there, but here it is as an equation, as a means of trying to find what that transmission angle is, or the extreme case, right? The worst case. So that's good. I think it's going to be the maximum and the minimum, but you got to be careful about what we consider to be the maximum and the middle. Now the idea though is the transmission angle is always between 0 and 90 degrees. Coming back again, the reason why we care about it is when it's a torque output that we're trying to get. This transmission angle is going to be a limiting, right, to how much torque that we can put out onto the thing. So we want to find the two instances where we're going to have. I think these are the worst case, possible worst cases, because the maximum is going to be 90 degrees, right? So that's going to be the condition. When this is 90 degrees from that, we're going to have the best situation that we can, right? In terms of transmitting a torque, and that's the idea, the transmission angle for here. They're also talking about non-Grashof triple rocker, right? So this was the Grashof one as it applies. So the non-Grashof one, we have possibility of having a transmission angle of 0, right? Because these things can be in line with each other, and then it can't transmit any torque. And they can also be in line with each other right here, where they're giving that this is the transmission angle, right? But it can't get past this anyway. So we have mu, and we have nu and mu, and where you can memorize or look up these angles or these equations for these angles, just be cognizant that this is law of cosines that we're really using right here. And it's true up to here. So it's nice to have these equations, but also to take a look at the fact that, like, here is a triangle, and we are able to get from law of cosines what that angle is going to be. And a similar thing right here. Here again is a triangle, and here is an angle right in there that's the interior angle that we're getting from this law of cosines. And lastly, before I went into a numerical example, I want to point out the concept of mechanical advantage. And you can really think of that as being the ratio of torques, of input to output torque. We want mechanical advantage, right? We can gain from having, or we can lose from the configuration, right? If we want a mechanical advantage greater than 1, we'll say that the mechanism is giving us an advantage, but it could be a mechanical disadvantage if you have a ratio of output torque which is less than input torque. But of course, what you're going to change when that happens is you're also changing the speed, right? So the ratio of the speeds is going to go down. So just like in gears, where if the gear rotates slower, right? If the output gear rotates slower, you've increased the torque, because torque times RPM equals power. And we're going to assume that there's no losses. So input power has to equal output power. So if you lose in torque, if the torque goes down, the speed is going up. If you're losing speed from the input to the output, the torque is going up. So just be advantage. It's good to take a look at that. The ratios, either the ratio of the torque in or torque out to torque in, or of the speed out to speed in. They will give you an impression of what the mechanical advantage is going to be. So, pause. Now, one of the resources that you might consider using here under useful links and resources is a book. I have a couple of them. This is also, Shigley was one of the authors. I'm going to pronounce him Wicker, I don't know. And Shigley, The Theory of Machines and Mechanisms. I have a 1981 version and a 2003 version that's posted on here. You can find it online pretty easily. So I'm not feeling too terribly bad about presenting it here. But if we were to look up, I think maybe if I do a Control F, I can go advantage. So you go, mechanical advantage is presented there as a thing, right? So here's mechanical advantage discussed, so you get the idea. Because it's not, I don't think it's really presented much in Norton's book. But we could check, can't we? Yes, okay, so in Norton's book in page 304, we do introduce something called MA, mechanical advantage, where you say the force out is divided by the force in. They do mention, okay, so I was saying it's torque out versus torque in. Personally, I think that's a better definition here, but they're saying torque out divided by torque in, but multiplied by R in and R out, right? And they're also saying we have the speed in and the speed out. So they're considering that the velocity ratio. So this is the definition according to Norton. Right here. In Shigley's book right here, so here's a more up-to-date edition right here of Shigley's book. Same guy as you'll remember from mechanical design class. You can see from here they're saying that it could be the ratio of the force or the torque exerted by the driven link to the necessary force or torque required by the driver, right? And they're even giving an equation here, and they're referring later to section 3.19. It's got a little bit of an issue with this equation right in here, I noted that this figure doesn't match up with what they use later on. I bring this up including in part because it's not, this discussion is not located here, and that equation is not located there in this section here. I got to wonder here, let me see, I'm going to go down and let's see, we'll go mechanical advantage right here. Here where they're considering mechanical advantage, you'll see that they have the ratio of the torques going on right there. And you'll see that beta right there. So we had to be careful with this analysis, but this indices of merit, mechanical advantage, is definitely something that we care about with respect to this. If we went to page 163, apparently, and I'm not sure if this is something I want to do during class time. Probably not, right? We have mechanical advantage discussed right there, yeah, and that's where we have that beta being presented right there. So you do have access to the earlier edition of this text. I would encourage you to look at that mechanical advantage as when we're doing an analysis here. So what I've said, according to this right here, okay, so I'll just go ahead and put this up here. According to this, we have a mechanical advantage that takes place based on the equations, and this is similar to a torque ratio, where this is the output link, and we're taking the sine of the differences of the angles, and then we're dividing by the input link, right? The crank length, and the sine of the difference between the two angles, right in there. So let me write that into there. Right. So I'll write mechanical advantage, but I want to put a star next to it because I think you have to double check that it isn't when it comes to these angles, that we're not dealing with a situation where we have an angle that's going to be, this should hopefully never be greater than 90 degrees. I think it will affect the results. Don't quote me on that, but I think that's true right here. So this is similar to torque ratio, but we want to be careful with this. So read the section carefully and double check on that. I have talked about toggle positions right in here, where and this brings up to section 412. So this is like a repeat in section 412 of what was covered previously in that other section, right, where we brought up the limiting conditions right here in section 3.3. It brings it up again in these toggle positions. And so I think I gave some of these equations where we're showing the overlapped and extended, and we're showing these Grashof triple rocker transmission angle issues. We also identify the toggle positions, right? So that's going to be slightly different, the toggle positions. So if we get asked for the toggle positions, you want to create you might need to create a triangle where it shows those toggle positions for non-Grashof or positions. So, and this right here, once again, you're applying. Okay. So we're finding this H as part of this, right? So there's a triangle right in here in H that we care about, and then there's a triangle right here, and so there's H kind of joins those things. So that's where they are combined. So what you'll need to do in order to sort this out is read the toggle positions section of this quite carefully. And one notable thing, by way of finding this relationship by equating that length h in here, is that they take the derivative of theta 2 with respect to transmission angle, setting it to 0. You're able to find the minimum and the maximum the possible transmission angles, and I think that's true. I take that back. Reading this closely, the only time that this is possible to be equal to 0 is when mu, that transmission angle, is either 0 or 180. We kind of knew that. I mean, that's sort of self-explanatory, but I guess that is demonstrating that the nature of that. So anyway, let me go and do a example. Hopefully I can do the examples. It's already, this video is too long already. Okay. So anyway, hopefully we can get to this. This is from the let me stop this and make the examples a separate video, because this one got too long.